I am hoping that you have given a try to solve this problem, and like most of the class examples, this is also very straightforward. Just to make the problem more precise, let me, this was understood because when we have multi-axial stress and strain. So, this will be effective stress and this will be effective strain. Okay, so, now we have this problem where you are given the flow behavior, this will be called the flow behavior, and you have to find out that after a given strain, the exact strain value is not given. What is given is area reduction. So, 0.3 area reduction, which means 30% area reduction. What will be the new yield strength or the stress value after that? So, let me draw a rough sketch of how this will look like. So, let us say we have a wire like this to begin with, and this is the wire after reduction. So, let us say this is L naught, this is LF final length, this is A naught and this is AF. Now, if we call this as strain 1 in this direction, this is not the, okay, let me not confuse you. So, whatever strain is happening in this direction is related to strain 1. So, now I can say that L naught A naught is equal to LF AF. Again, this comes from volume incompressibility. The volume cannot change. So, the total volume over here is same as the total volume over here, and remember we are talking about wire drawing kind of operation. So, this is, you can assume, circular in shape. Now, if I want to get epsilon 1, it will be equal to ln LF by L naught, but LF by L naught is what? Is related to, or is equal to ln A naught by AF. What you are given is, now remember these are, I am doing it in a very small step by step, but when you are solving it, these steps can actually, you can ignore these steps, you can these things would be known to you and you can come directly to some of the or second step or next step. Now, here if we have this, now R is given, which is nothing but A naught minus A by A naught, and this is given as some value. Okay, now, this is 1 minus A by A naught, A is actually not AF. So, our A naught in terms of R becomes 1 over 1 minus R. This is from here we can get this, and therefore, epsilon 1 is equal to, we have this in ln. So, next time when you see area reduction, you can straightforward say that strain 1 would be equal to ln 1 over 1 minus R. So, that is what I meant, that this time to show the steps explicitly, I am doing all each and every small steps, but in future when you are trying to solve, you can come directly to some of these and you need not go through each and every step. Now, that is not all. What about epsilon 2 and epsilon 3? They will be equal, and it will be equal to minus epsilon 1 by 2. Why? Because we have to have incompressibility, which is epsilon 1 plus epsilon 2 plus epsilon 3 equal to 0. So, when you put this together, you remember we also did the same thing for tensile test, and over there we saw that this implies epsilon bar is equal to epsilon 1. What about sigma? You have sigma 1 not equal to 0 and other two sigma are actually 0. So, from here now you can just directly calculate, which will be equal to 1 over r is already given, which is 0.3. So, what you will get is actually 0.357. So, this is the strain value that we were interested in, and you put it in that equation, sigma bar equal to 500 into 0.357 to the power 0.5, and you will get something like 299 megapascal. So, what it is saying is that if you have reduced the wire from this size to this size, earlier you may be requiring much lesser yield stress, but after this reduction you will require a higher yield stress, something like 299. Do not get confused by this 500. This 500 does not represent any physical value, it does not represent the original yield stress or something like that. The original yield stress of the material must have been much lower than 299. It is now increased after the cold working to 299. Now, let me give this problem a little bit of twist. Instead of wire drawing, let us say that it was a rolling operation. How would things change? Now, if the operation was rolling instead of wire drawing, what are the things that change? So, what about sigma 1? Sigma 1 still is not 0, sigma 2 equal to sigma 3, they remain 0. So, the stress part does not change, implies effective stress remains equal to sigma 1. However, when we look at the strain part, here in the rolling we assume that epsilon 3 is equal to, which is in the perpendicular direction, transverse direction is equal to 0. This implies that epsilon 2 is equal to minus epsilon 1, and therefore, if you apply the rule for effective strain, what you get so here we have epsilon 1 square, epsilon 1 square. So, this is 2 epsilon square. So, 4 by 3 epsilon 1 square, and this is 0. So, this comes out to be 2 over root 3 epsilon 1. Now, the epsilon 1 value that what we calculated over there as 0.357 was actually epsilon 1, and therefore, effective strain is now equal to 2 by root 3 into 0.357. Now, the effective strain has actually increased, or in terms of when you are doing the rolling operation with same amount of area reduction, the effective strain value is higher, and it is equal to 0.412. And when you put this to get the effective stress, what you get is 500 into 0.412 to the power 0.5, and this comes out to a little higher value, of course, because the strain was higher. So, if you were assuming wire drawing kind of operation, the yield stress after that kind of area reduction is 299, and yield stress after this kind of area reduction in rolling comes out to be 320. If we assumed same effective stress in both of them, then there will be no change. So, you have to be careful. What we are not saying that for the same effective strain, rolling will give you higher yield stress. What we are saying is that same amount of area reduction, strain is higher in rolling compared to wire drawing, and because of that the yield stress value that you obtain here is higher. So, we have looked at stress strain and stress strain behavior quite a bit. Now, it is time to move on to another parameter that is important to deformation. And now let us look at this another parameter of deformation. Can you guess what it would be? It is strain rate. When you first hear that, if you are hearing the word strain rate for the first time, you would assume that it has only to do with the rate at which the material is deforming. And it should not make much of a difference to the overall stress required for deformation or to the material behavior or the material properties, but that is not true. First of all, let us understand what is strain rate. It is usually denoted by dot over here, because dot represents del epsilon by del t. So, it is actually in that sense rate of strain, or we can say rate of deformation. To get a feel of it, again we will take help of uniaxial tensile stress. Let us say in uniaxial tensile test, the displacement rate of the wedges which hold the grips so the rate at which it can move is 10 millimeter per second. Okay, so remember, this is never the unit of strain rate. So, never confuse that this displacement rate is same as strain rate. I have to explicitly mention this because I know that at early stages students do get confused and put strain rate in terms of millimeter per second. It is not the unit of strain rate, it is just the displacement rate. From this displacement rate we will get strain rate. Now, let us say the gauge length of your sample is, for the first case, let us say it is 10 millimeter. So, the sample is small and your gauge length is 10 millimeter. So, the whole deformation is occurring in that 10 millimeter length, and your displacement rate of the wedges is 10 millimeter per second. So, all the deformation that is taking place is getting divided in that 10 millimeter, and therefore, the strain rate is actually given by 10 per second by this 10 mm, which is 1 per second. So, this is actually the unit time in inverse time, that is the unit of strain rate. Now, let us say the gauge length is 100 millimeter, you are taking a much larger sample, then strain rate is equal to 10 millimeter per second by 100 millimeter, which is 0.1 per second. So, the larger the sample, it is getting divided into a much larger length, the displacement rate is getting, you can say, absorbed or distributed for in a larger length, and therefore, the strain rate comes out to be smaller. So, that is what is strain rate, the rate at which the straining is occurring. Straining is occurring in that whole gauge length, and that is what divided it by the whole gauge length. Now, why should we at all be concerned with strain rate? Why is it a consideration? Meaning, what kind of influence does it have? So, it may not appear by intuition, but when you are talking about strain rate also influences your flow behavior. specifically if you increase the strain rate, the flow stress increases. You can do a very simple experiment at home. Take a polythene bag. Now try to stretch it very slowly. You would see that you need a very small amount of load to stretch the plastic. Now in the second attempt, take a very similar plastic, or if you can divide it, the same plastic in two parts, so that you can do two experiments. In the first one you have done this at very slow rate, where you will experience that you can deform it very easily. In the second one, try to do it in a snatch, just try to break apart. So you would see that the same amount of deformation, the second one will require a much higher strength from you, a higher load from you. So that translates to higher stresses requirement. Now the origin of this increment in stress, flow stress, because of increased strain rate is different in different materials. For in crystalline materials it is different, and in plastic that I just described it is different. However, you can get a good feel of what or how the strain rate can influence the flow stress. The simplest way to express this is this relation, a relation very similar to what we have already seen for stresses. Now this time, instead of stresses, instead of strain over here, what we have is a strain rate. So this is one quantity, strain rate, and M is your M is strain rate sensitivity. And C is called strength constant. How much this strain rate will influence the flow stress. So this is the stress required for flow behavior, meaning you can again say this is the yield stress of the material after given deformation. So how much different flow stress is required for a given amount of strain will depend on this value M. And you can say, fortunately for us, this M is usually very small, of the order of 0.0 to 0.03, but that is only at low temperatures. At higher temperatures, the value of M increases drastically, and we will see a schematically how this M changes. But for now it is suffice to say that M is much larger at higher temperature. Now what is the significance of this very small value of M? The significance is that if you increase the strain rate, if the strain rate is increased by, let us say, 10x, 10 times, even then a very small change in flow stress is observed. And because of this, you would see that most of the time when people are talking about metal forming, metal working, then strain rates are usually given on a log scale, because you change strain rate by, let us say, from 10 to the power minus 3 to 10 to the power minus 2, 10, 0.1, 1, 10. So you change it in orders by factor of 10. You do not change it just by, say, from 1 to 2 or 2 to 3. In that case you will not see you will see almost no change on the flow stress. Only when you change the strain rate by some very large factor, 10 or 100, that you would see its influence on the flow stress. Now we will solve one example related to the strain rate to get understanding of what is the importance of this. So let us in automotive industry, you know that people are always trying to reduce the weight of the car, because reducing the weight of the car leads to improved mileage, which is a very important goal of the automotive industry. Now, how do they reduce the weight? They use materials which have higher strength. If you have materials with higher strength, you can use even a thin gauge of the material and do with even less weight material. And of course, the other way is to use material which have low density. But low density material like titanium, they are very expensive, even magnesium, they are very expensive. And so, the thing that people apply is taking steel itself, but with higher strength. So, let us say we have two different materials, low carbon steel, which is currently used in most of the automotive industry, by it is to be replaced by high strength low alloy steel. So, that is the target. You want to reduce low carbon steel by high strength low alloy steel. Now, how much will the gain be, or how much will be the change in the weight? That is what we will measure or try to gauge from here. Now, let us say Y1 or the yield strength for this material is given as 240 megapascal, and Y2, this certainly is a much higher strength material and it is 420, because if you are replacing this by that, it must be that it should have higher strength, and both of them are steel. So, mostly iron. In that case, the density for both of them will remain same. So, the density of the material is approximately same. So, if you take same volume, then the weight of both of them will be same, but then you will be able to apply much higher stress over there, because the yield strength is higher. So, you would what you would do, ideally do is you will have much thinner gauge of material when you are using second material. Now, here let us say this yield strength for both of these were obtained at a strain rate of 10 to the power minus 3 per second, and you have also measured the strain rate sensitivity. So, here the strain rate sensitivity is 0.03, and in this case the strain rate sensitivity is 0.01. Now, the first question is that if you were assuming that this is the strain rate that is required, how much weight percentage you will gain. Okay. So, let us say we have T2, which is the thickness, Y2 is equal to T1 Y1. How do I get this? Because if I am using if I am replacing one material by the other, then the load that is being carried by that material must be the same as the load being carried by this material. So, let us say whatever thickness T2 was for this material and T1 is the thickness of this material, then the load carrying capacity for both of them should be same, and that is why I will reduce the thickness for that one. So, given that T1 is the thickness of this one and T2, so this one in this particular case T2 should come out to be thinner. Now, we can say T2 by T1 is equal to Y1 by Y2. Now, since we have already said that density is same, therefore, the weight for the two should also be proportional to the thickness ratio. So, W2 by W1 will be equal to T2 by T1 equal to Y1 by Y2, and here you can put in the values and get 240 by 420, which is equal to 0.571. So, what it is saying is that weight of the second material is only 0.57 of the weight of the first material, and still it will carry the same load, or it will be able to bear the same load. Therefore, at a much thinner gauge or at a much lower weight, you are able to get same kind of performance, which means that how much are you saving? you are saving 1 minus 0.57, which is equal to 0.429. So, the weight saving is equal to 42.9%. So, you are able to reduce the weight of that particular component. I am not talking about the whole car, but for that particular component, if you change from this material to this material, you have reduced the weight by 42.9%. Not only that, even so that will lead to, of course, improved fuel efficiency, less pollution, but also lower cost, because both of them are steel based alloy, and probably this is not as much expensive compared to this one. So, by reducing the weight, you have also cut down on the cost. So, that is the aim or the goal for most of the automotive industries as of now, because they are under severe clock to reduce the weight and improve fuel efficiency and so on. So, that is one part of the problem. Next part of the problem is that here we assumed strain rate equal to 10 to the power minus 3, but in reality when the crash takes place or when the car crashes, the strains are of the order of 10 to the power 4. Now, you see how much is the difference from this strain rate to this strain rate. It is 10 to the power 7 times higher. So, that must make a difference to the yield strength of the material, and therefore, we will have to do a calculation again. Now, you will have to do this calculation assuming that the material deforms at a strain rate, sorry, this is not a strain, this is strain rate, just like here. So, this is you will have to do the calculation assuming that the strain rate is equal to 10 to the power 4, and I will leave it to you over here to again try to solve this on your own, because next step is again, like I said, just plug in the values and you would be able to get the answer. I have already given you the steps for this one. The next step, all you have to do is, for this strain rate, calculate the new yield strength for the two materials, and then with the new yield strength again calculate what will be the weight ratio. Now, just looking at it, what would you think? Would the weight saving increase or weight saving should decrease? Now, here what are the things that you should look at? Should you look at the strain rate from where to where we are going, or should you look at this value? Now, what you notice here is that this m value is smaller than this m value, which means that at higher strain rate this will not increase as much, but this will increase by a larger fraction, and therefore, what it would mean is that the difference between the yield strength for the two would not be as much as you see right now, which in turn would imply that the W2 by W1 ratio should decrease. Whenever you look at a problem, you should try to get a feel of it, so that when you get the answer you can cross check it. So, from this, when you solve it, what you should get is a smaller saving in weight percent. So, try to solve it, and anyways I will be solving it in the next class, but it will be a good experience for you trying to solve it. So, I will leave you with this problem and we will come back on it in the next class. Thanks.